So, state space modeling of the micro-hydroelectric dam that we modeled last time with a linear graph. Let's try to model it with, there we go, with the state equation. It's going to come from the linear graph, which we found last time. There's a nuance here. R1 is now combining what was R1 and R2 in the linear graph we drew in last year. That's just convenience. We can combine those two. Bring of the R's, so sorry about that. So let's go ahead and draw the normal tree, which we can just superimpose on this. We always begin, well, it's like really thick, with the across variable sources. So the pressure sources for a fluid system. Flow sources through variable sources, we do not include it. And then we go to our A-type energy storage elements. C1, Ca, the moment of inertia, C3, the capacitance of the battery that we're charging. And then we go to transducer elements. So the trans element that goes from 3 to 5 DC generator, and as with a DC, it is a transformer type of transducer, which is to say its across variable is related to the across variable on the other side, and the through variable is relayed directly. So this is a transformer. Let's check out the turbine model. So here is a model for a turbine. It's linearized, and as long as you're around some operating point or along some flow drop across the turbine, then this is approximately true. So this is a decent model, and notice that this is a through variable, cross variable related to an across variable, which is to say it is a transformer. So, transformer model for each, when we select the elements for a normal tree, we have to select one of the trees. So, remember, we can never create a loop when we select branches for a normal tree, so we can't select two. That means we must select one. Remember, the one caveat for transducer elements is that we want to select the least number of t-types in the normal tree with our selection. So let's go ahead and see what happens if we choose. We also have to choose this guy because we can't create a loop with choosing 3. So we don't really have options, so we don't really need to do any analysis of the minimization of our t-types in the normal tree. Have any in the normal tree on this one, so it wouldn't be a big deal. So we go down to D-type, which are our fluid resistors, and that's as many as we can get in the fluid side without creating a loop. So that part's done. Can't select any here, we create a loop. B is D-type, but we can't select it because it would create a loop with J. R3, the resistance and the windings of the generator. That one can be selected, and then we can't select R4, otherwise it would create a loop there. If we selected any more branches or any more elements brought into our normal tree, we would create a loop. So we're done. And so then we're ready to write our elemental equations. So, let's also talk about our variables. So there are 6 independent energy storage elements making it a 6-order system. The 6 are C1, C2, L1, J, and L2. So 1, 2, 3, 5, C3, 6. So we take to be our state variables across variables on A-types in the normal tree and through variables on T-types not in the normal tree. So PC1, PC2, cross variables of A-types in the normal tree. QL1, that's a through variable of a T-type not in the normal tree. Omega J1 is an A-type, so cross variable L2 is through, and it's a T-type. C3 across A-type. And then our inputs are the pressure source PS1, PS2, and our flow source QS. So then we're ready for our elemental equations. So we write this, it's a huge table. So for each element, we write an elemental equation, and 3, 4, 5 times 3 is 15. So there are 15 elements. The transducers have 2 equations each, and that's the solve. The other half come from the continuity and compatibility equations. So continuity and compatibility equations can be found in the usual way by drawing contours and temporarily creating loops by including links in the normal tree. We proceed by drawing a table of all continuity equation for each branch of the normal for each link. So sometimes we separate the continuity and compatibility as separate to combine them into a single table with each of the elements and write either a continuity equation for equation, depending on if it's in the normal tree or not in the normal tree. So for instance, C1 and C2 are in the normal tree, and we write compatibility equations for them. L1 is not in the normal tree, as you can see from here. L1's not, so we write a continuity equation for it. So that is, that is a compatible. I said that C1 and C2, if they're in the normal tree, they get the equation. If they're not in the normal tree, they get a compatibility equation. So L1 gets a compatibility equation. My apologies, I totally inverted that. So we have our other equations to write down. Bam, bam, bam. So that's another